You are seeing multiple neural networks learn with the same settings, except for one tiny difference: activation function. And by the end of the video, you will be able to figure out which network uses which activation function. We will wrap up with a finale showcasing networks evolving with diverse activation functions. Oh boy, I enjoyed animating this. By the way, this is a comment recommended video. If you also want 101 of any AI concept, let me know in the comments. Before diving in, let's briefly take a sneak peek on neural network. For extended understanding, watch my previous videos.
That I can do!
Hey, not now. So, neural network is a giant mathematical function of nodes and weights connected in layers with activation functions that map the input data to the output data. But what the fish is an activation function? Picture activation functions as the traffic lights of a neural network. A green light allows the input to move forward, a red light stops the flow of information, and a yellow light compresses some of the information before passing it on to the next layers. These nuances introduce a notion of non-linear modeling, crucial for mimicking real-world situations. Without activation functions, modern AI would not exist at all. Take this dataset as an example. To accurately define its boundary, we need a curve, not a straight line. Imagine a ball stopping linearly. It just looks odd, right? Adding a bit of non-linearity to it improves its motion.
Yeah, I like that. Yeah.
For a simple neural network with two input nodes and one activated output node, model output y hat is the sum of input times the respective weight. And that's not it. This sum then goes through the activation function sigma, which is the network's final output. But with millions of possible functions, how do we choose the right activation function? Today, there are over 50 activation functions. We'll discuss the top 10, which majorly fall into trainable and non-trainable type. I would divide these two into two more subcategories: linear-like and S-like, where S stands for
Sexy.
Yup, the one that curves. Kicking off with S-like non-trainable, first one is the sigmoid activation function, stemming from the statistical theory of logistic regression and the oldest of all. It squishes every value between 0 to 1, hence acting similar to the yellow light for positive inputs and red light for big negative inputs. By the way, most of the S-like activation functions follow a similar pattern. However, the derivative of sigmoid can go up to 0.25 only. It faces vanishing gradients problems, extensively explained in my previous video on backpropagation. Next up is Tanh, with the following curve. It scales the value down in the range of -1 to 1. This scaling makes Tanh advantageous for neural network layers that need to deal with negative inputs in a symmetric way around 0, unlike the sigmoid function. And the max derivative is 1, which is better than 0.25 of sigmoid. On a side note, Tanh mathematically is actually a linear transformation of sigmoid, hence they are almost equivalent. The last two in S-like non-trainable are Softplus and Mish. I know that's a lot of maths, but
Math is elegant.
just observe the curves for an intuitive understanding. That right long tail of Softplus you see ensures a positive flow of gradients all across, just like a green light. This flow was lacking in both sigmoid and ReLU. But Softplus doesn't treat small negative values well, and therefore Mish. These mathematically approximate better but are rarely used for deep nets because of high computation. Coming to linear-like activation function, it has a sharper transition than S-type activations. The most widely used now is the ReLU activation function. It's the fastest to compute and maintains a good derivative overall. Do you see this sudden flat line? Not good. Sometimes, small negative values can be more important than big ones. Therefore, Leaky ReLU and Exponential ReLU. Moreover, the value alpha is a hyperparameter set by the developer in advance. But wait, why not let the model itself find the best alpha?
That's smart.
Yep, that's possible. This leads us to the trainable activation function category, Number 1. Parametric ReLU. Let the alpha in Leaky ReLU be learned automatically, and that's PReLU. Similarly, transform Sigmoid by multiplying it by the input itself with the learnable parameter beta, and you get SILU, introduced by Google recently. These solve dying ReLU, vanishing gradient, and negative value issues, but can be heavy on your machine. Next, as promised, you can see the activation functions aggregating to generate non-linearity. On the left side is ReLU, the sharp edge one, remember? And on the right side is Sigmoid, the smooth one. Magical. Hopefully, now you can guess which of these is trained by ReLU and which one by Sigmoid. I did not cover softmax. I think it needs a dedicated video on its own. Till then, keep watching Bias versus Variance for AI in depth. See you for the next one.